All right, hello and welcome to another video. This video might be a little bit longer because there is some required knowledge um, that I want to go over before starting the problems in this video. And yeah, and that is the different types of transformations that we can have in functions. I would also like to mention that I have a longer video that goes into more detail from a previous term that you're welcome to watch. I will try to link it here in this video, but you can also search around on my channel to find it. It's called, like function transformations. Okay, so let's go ahead and take a look at the different types of function transformations, um, and and then we'll jump into the problems. Okay, so suppose we have a function. Let's call it y equals f of x. And actually, let me change this to blue. Y equals f of x. If we want to shift this function in the upward direction, just straight up, there is a way that we can do that by modifying this function, f of x, and that is by adding some value k that is greater than 0 to the function. So here in this little example, I have f of x plus 2. So for example, this is actually the function is f of x equals, and let's see, the colors might be a little bit off here. But the original function is f of x equals the square root of x. That's what the square root function looks like. And then I graphed, uh, let's call it, well, yeah, actually we can call it f of x plus 2, which is just the square root of x plus 2. If you see this function here, we can know that that is just the basic square root of x function, sometimes called the parent function, and then it's just shifted up 2 units. In a similar way, if we were to subtract 2, then um, that graph would just be shifted down. Okay, so this is advantageous for us because if we know what the square root of x looks like, which there's a couple of points that we know on this graph for the square root of x, and they are 0, 0, since the square root of 0 is 0, 1, 1, since the square root of 1 is 1, and 4, 2, again, since the square root of 4 is 2. These are points that are on this graph. And so if we want to quickly sketch the square root of x plus 2 in green, we can just take these 3 points and shift them up 2 units to 0, 2, 1, 3, and 4, 4. And we now have our new graph, right? We can sketch our curve. So function transformations allow us to analyze other functions that are more complex by knowing the parent function well and knowing how how that parent function is transformed to give us the new function that we're dealing with. Okay, so it also helps us to graph functions very quickly. All right, so as I mentioned, this is going to be like a quick overview of these function transformations, and you can watch the longer video that I go more in depth into the different types of parent functions, and then I kind of take my time graphing them. Um, so feel free to watch that video if you want to know more. And so I've actually also gone on Desmos.com and created this little just app or whatever you want to call it. Just to kind of show here, if we take the function f of x in blue, f of x equals the square root of x, and then I've created this f of x equals, or so this new function called f of x plus a, or plus k if you want. I said that if you add a positive number to this graph, it's going to be shifted upward, and we can see that here, right? This green graph, the parent function is in blue. As I increase the value of a, this graph just gets shifted up more. And then if we decrease the value to some negative value, so we subtract some value from the function f of x, then this function just gets shifted in the downward direction. Um, yeah, so not too uh, surprising. That's what we said on our previous slide. Okay, so just so we can kind of see what's happening, this uh, adding or subtracting of a number outside of the function is a vertical shift in the up or down direction. All right, so let's move on to horizontal translations. So assuming that h is a positive number, Now, if we take our y equals f of x and we add a number, notice that how that number is added. It's inside of the function f of x plus h. The plus h is in the function. Since this is a square root function, this is going to look like, uh, well, we said f of x. The basic function is just the square root of x, the parent function. So what I've shown here in the graph is uh, f of x plus 2. Notice how the plus 2 is not outside of the function. We're not adding 2 to the function itself, to the entire function, but we are putting a plus 2 inside of the function. In terms of the notation, that's going to look like the square root of x plus 2. Right? Those sound the same, but it's the square root of the quantity, the entire quantity x plus 2, not the square root of x and then plus a 2 outside of the square root, but the square root of the quantity x plus 2. Okay, so what is this going to look like? Or, well, if we add a number inside of the function, then that is going to shift the graph to the left h units. And so we can actually see that the blue graph shifted 2 units to the left to give us our new transformed graph. So the points that we said earlier, they were 0, 0, 1, 1, and 4, 2. Each one of them has been shifted to the left 2 units to give us our new graph. Okay, so we can see how if I saw this function myself, I would say, well, that's just the square root of x shifted to the left 2. I know what the square root of x looks like, so I can graph this function very quickly without really having to do any computations. All right, so can you guess what this function would look like? What if we did f of x minus 2? The square root of x minus 2, what would that look like? Well, that would be a graph shifted to the right 2 units. And to see that, we can go back to our Desmos little demonstration here, put plus a inside of the function. And if a is equal to 0, okay, well, that's just the parent function. But as soon as we add a positive number, notice what happens. It shifts to the left. Okay. And then if we subtract a number, well, it shifts to the right, some number of units. Okay. So this is a horizontal shift. All right, we're going to use all of this information in just a moment. Okay, well, that's sliding up and down, sliding left and right. We've seen both of those. What other transformations are there? Well, we can flip a graph or reflect it about the x-axis. And the way that we do that, if we start with the function y equals f of x, well, f of x just represents the y values of the graph. The y values are, some positive or non-negative numbers, 0, 0, 1, 1, and 4, comma 2. What we're going to do is, and remember these are x values, and then the output value, sometimes are thought of as y values, or f of x values, function values, or values of the function. What we're going to do is we're going to write a new function. This new function, sometimes it's called g of x. This is going to be the opposite of f of x, or a negative times the f of x function. Well, if we multiply the function, the y values, by a negative, it's going to reflect these points and put them on the other side of the x-axis. So the x values stay exactly the same, but the y values all become their opposite. 0, comma 0, well, if you put a negative 0, that's the same thing as just 0. 0 is neither positive nor negative. So if you multiply it by negative, it just stays 0. Okay, and so that's how we get a reflection. So we should recognize whenever there is a negative in front of our function, that is going to result in a reflection about the x-axis. Okay, so let me just write it again. F of x equals, oops, and that's not the right one. In blue is f of x equals the square root of x. Okay. If I were to write negative f of x, or if you see the opposite of the square root of x, well, here, since the negative is outside of the function, it gets reflected vertically about the, vertical up and down about the x-axis. Okay. It's similar to how we had the plus 2 outside of the function. That was a vertical transformation, right? Um, so here, this is vertical as well. So how do we get a horizontal reflection? Well, how we got a horizontal shift earlier was to put a number inside of the function. To get a horizontal reflection, it's going to come in a similar way. When we have the function f of x equals the square root of x, if we want to reflect this horizontally about the y-axis, then we're going to look at f of negative x. We'll put that negative inside of the function. So this is going to look like the square root of negative x, or the square root of the opposite of x. Okay, that's what is going to result there. So let's go ahead and take a look at that here on the graph. Well, right now the blue and green graphs are the same. As soon as I put a negative out front, reflects it about the x-axis. If we put a negative in front of inside of the function, it reflects it about the y-axis. It's a horizontal reflection. Okay. All right, very good. And let's move on. There are just two more. Um, these are the other kinds of transformation, and they are stretches. We can stretch a function vertically or compress it vertically. So just imagine grabbing that square root function and just stretching it up and down, or compressing it. Excuse me. What is that going to look like in terms of the function? Well, if we stretch it vertically, we're changing the y values. So we are going to multiply the output of the function f of x. So let's go ahead and take a look at one of these graphs here. Um, and we'll look at the statement. Okay, we start with the original function, y equals f of x. We're going to multiply f of x by some value. Now, it really depends on what that value is. The value is going to determine whether it's stretched or compressed. So the function f of x is going to be stretched vertically if a, that multiplying factor, is larger than 1. Okay, so here we have f of x equals the square root of x. And so if we want to make f of x twice as large, remember we had the point 4 comma 2. If we want the output to be twice as large, we can just multiply f of x by 2, and that will give us the new point 4 comma 4. Right? This y value became twice as large. The way that that happened was changing f of x, modifying it to be uh, 2 times as large as f of x, 2f of x. So that would look like 2 square roots of x. That function is graphed there in green. You can see, hopefully you can see that it's shifted to be twice as tall. The point 1 comma 1 becomes, or is transformed to become the point 1 comma 2, or is stretched vertically. 0, 0, well, 0, that's twice as large. 2 times 0 is 0, so that point stays there. But every other point with a non-zero y value becomes twice as large. Okay, so hopefully you can see that stretch there. Now, if you look in our textbook, you could also say that there's a vertical stretch when a is less than -1. Uh, But you also want to keep in mind that when a is less than -1, it's going to be negative, and therefore um, it's also going to be reflected about the x-axis, as we mentioned earlier. If you multiply by a negative, that's going to cause a reflection about the x-axis, and if a is less than -1, it's going to stretch it in the negative in the vertical direction. Okay, so let's go ahead and take a look at the next one. What about uh, for vertical compression? How do we compress a graph vertically? Well, if you think of the vertical stretch as being multiplied by a factor of 2 or 3 or something large, to get to stretch it twice as or large, um, well, we can also just think of it as dividing, cutting down our graph in size. So dividing it by 2 or multiplying it by a half, we want the graph to be half of its size or an eighth of its size or some fraction of its size where that fraction is less than 1. We want it to be reduced in size. So we're still going to multiply the function by some number. That number, though, is just going to be, um, a small number. So it'll be close to 0, less than 1, but greater than 0. Now, I need to correct here just for the negative number's sake. We could also have, like a -1/2 that will also reduce it or compress it vertically, but keep in mind that it's also going to reflect it about the um, x-axis. Okay, so these numbers, when I say between 0 and 1, that's going to compress it, but we could also have the negative of those numbers. It's also going to compress and reflect. Okay, so let's go ahead and see. Um, f of x is equal to the square root of x. That's the blue graph still. And so our new function is going to be, I believe I graphed 1/2 of f of x, or 1/2 of the square root of x. Okay. So the square root of x becomes, the outputs are now going to be half their size. And you can actually see by plugging in a number like 4, 1/2 of the square root of 4, that's 1/2 of 2, which is half of 2 is 1. So the output of 4 is now not 2, but half of 2, which is 1. And so we can see that the point that was 4, 2 in the parent function becomes, the y value gets reduced to half of its size and becomes 4, 1. Yeah, here's 1 right there. The point that we knew as 1, 1 before gets mapped, re you know, placed in a new place. The x value stays the same. The only thing that we're changing is we're multiplying the y value, the square root of x, by 1/2. So the y values all become half of their size. Okay, and so hopefully you can see this whole function just reduces to half of its size. Every single point, the y value gets cut in half. Okay, so let's go ahead and take a look at this on Desmos. We will put, so let's go ahead and put a to equal 1 here, and we'll put oops, the a on the outside. So we said that if we want the graph to be twice as large, we can increase a. So here's the function that 1.5 times its size in terms of the y values, twice its size, 2.5, 3. You can go as large as you want. Okay, the function is being stretched in the vertical direction, in the y direction. Okay. Now, what if I take this number to be less than 1, but still greater than 0, so between 0 and 1? Well, here's a half, and actually I don't have, let me go ahead and put different values between uh, 0 and 1. So here is a bunch of values. So we can see at a equals 1, it's the same as f of x equals the square root of x, but we can cut it down to any fraction that we want, any fraction between 0 and 1 will produce, just a cut down version of the square root of x. Now, if a is equal to 0, well, that's just 0 times the function, which is 0. That's just line y equals 0. But we said that what if we were to go into the negatives? Well, if you go to negative 1/2, then it's going to be um, the square root function cut down to half of its size and then reflected about the x-axis. Okay. At negative 1, we discussed this one earlier. That's just the reflection. Here, since a is equal to 1, it's 1 times its size, which is just exactly its same size, but reflected about the x-axis. Okay. So there we can see. Um, and if we were to change this from negative 5 to 5, we can stretch it vertically in the negative direction if our value of a is less than negative 1. Okay. So that's very nice to see. Stretch it in the positive direction. Here's compressed, compressed, stretched in the negative direction, compressed in the negative direction, and so on. Okay, so nice. Um, that's if you multiply a factor outside of the function. Okay. All right. Very good, very good. Let's and I have a couple examples in that third graph, but we already talked about those. The last one that we're going to talk about is um, horizontal stretches and compressions. So we can stretch a function vertically or compress it vertically. We can also stretch it horizontally or compress it horizontally. Now, this is going to, yeah, well, let's talk about the horizontal stretches and compressions. This is kind of opposite of what it was um, what it was in the vertical stretches and compressions. If the number, it's a little bit counterintuitive, but similar to how we said if you subtract a number outside of the function, that's going to go down. In the vertical, it kind of makes more sense to me. I think it's more intuitive, but subtracting makes the vertical translation go down. But subtracting inside of the function, you might think if we're talking about horizontal, subtracting seems like it should go to the left, but it actually shifts to the right k units, right? We talked about the addition one. Addition shifts to the left. Subtraction shifts to the right. So it's a little bit counterintuitive, at least I think. In a similar way, um, I think the vertical stretch and compression makes the most sense. If you want to stretch vertically by a factor of 2, you want it to be twice as large, you just multiply by 2, a number that's greater than 1, right? So 2. Here, if you, we're going to put the um, multiplying factor inside of the function, as has been for all of the horizontal transformations. We're going to put it inside of the function. If you actually multiply by a number that's larger than 1, like say 2, is that going to horizontally stretch the function? It turns out no, it's actually going to do the opposite. It's going to compress by a factor of 2. Okay, so if you want more of an explanation for why this is, I do believe I cover it in my previous video. So I'll try to link that, in the description of this one, or if I can figure that out. Um, Okay, so let's go ahead and take a look. We could at least just recognize when this happens. So here we have y equals the square root of x in blue. That's the parent function. And so in green, we have y equals the square root of 2x. So here I put that 2. It's a large number. We can make this 10 if we wanted to. Well, it would actually compress it horizontally by a factor of 10 to bring it to 1/10 of its size in the horizontal direction, or half of its size. So what happens here, and we can actually make sense of it very quickly here. The point 4 comma 2 Well, yeah, let's look at y equals the square root of 4. If we plug in 4 to the parent function, well, if I plug in 4, the square root of 4 is 2. So I get the point, 4 comma 2. Now, what about when I transform it? When I put this multiplying by 2 inside of the function, what is that going to do? What it does is it actually changes the x values that produce equivalent y values. So let's suppose that from this function, y equals the square root of 2x, I want this value of 2 as my output. I want to see when am I going to have a y value of 2 from this new function in green? Well, I'm going to have a y value of 2 when the radicand is 4. Well, since I'm multiplying my x value by 2, what should my new x value be in order to get a radicand of 4? Well, I don't need x to be equal to 4 as I had in the past that produced 2. Now I only need an x value half the size because I'm about to double it and then take the square root. Okay, so we only need to plug in 2, half of the x value as before, to produce the same y value. And so this becomes the square root of 4, which is 2. And so we get the ordered pair now. When I plugged in an x value of 2 into this new function, I got a y value of 2. So notice what happens here. The x value gets cut down by a factor of 2, or to half of its size, and gives me the point 2, 2. All right, so similarly, let's do one more. Well, let's say here for this point, which was 1, 1 before, the point 1 comma 1. Well, to get 1, 1, for the old function, we had to plug in 1. The square root of 1 is 1. So the input of 1 produced the output of 1. So if I now want to produce an output of 1 in my new function, what x value would produce that? Well, um, the square root of 2 times what number? I need to get the square root of 1. So the x value that's going to make that occur, or the x value for which I will get a 1 as my output, is going to be half of the x value that I used in the parent function. Half of 1 is 1 half. So the ordered pair here is 1 half comma 1. So notice that the x values, when we put a 2 inside of the function, that 2 requires the x values to all be half of their size as before to produce the same y values. So if you want the y values to stay the same, you're going to need to use an x value of half of its size. Okay. All right. Good. And so in practice here, let's say we're looking at a table, so I don't want to get too deep into this. Again, I have another video and I should have watched it to know. I haven't seen it in a couple of years. But the xy table for the square root function is 0, 0, 1, 1, and 2, 4. And then we could go to 3, 9 if we wanted to. This is for the basic square root of x. Y equals, so if I were to make a new table, let's suppose I wanted to graph x and then y, where y is equal to the square root of 2x. Well, what's going to happen here is if I want to keep the same y values, basically all of the x's are going to get cut in half. So if I want to maintain the same y values, 0, 1, 4, and 9, the x values are going to be half of 0, 0, half of 1 is a half, half of 2 is 1, and half of 3 is 3 halves. Okay, and we can, oops, what am I doing here? Yeah, I have this uh, mm, kind of flipped here. So let me go ahead and erase a couple of these values. Yeah, these do not match up the regular square root function. Yeah, something was not making sense. If you want to see, kind of how I caught the mistake there, you can actually try plugging one of these x values in, and if you plug in 3/2 into that function, you're going to get the square root of 3, which is not 9, right? So that's, we can see that that's incorrect. They're just flipped. So let me flip them around. So what are the x and y values for the square root of x? If x is 0, 1, 4, and 9, then the y's are just the square roots of the x values. So y is going to be 0, 1, 2, and 3. And so if we want to preserve these y values, 0, 1, 2, and 3, what numbers do we have to plug in? Instead of plugging in 4 to get a y value of 2, I need to plug in half of the 4, which is 2. Half of 9 is 9/2. Half of 1 is 1/2. So I'm just taking this set of x values and dividing them all by 2, because I know that this transformation here is a compression by a factor of 2, or it cuts down all of the y values by 1/2. All of the x values by 1/2. So I just divide the original parent function x values, divide them all by 2, and that will be, this set of points will produce my new transformed graph. Okay, we're going to use this idea in a later problem. So let's yeah, so let's go ahead and um, yeah, we'll just kind of look at that idea there. We can check if this is now correct. If we plug in 9/2 into this function, notice that the 2's will cancel and you'll get the square root of 9, which is 3. This is now correct. Okay, so um, that was a lot there to say that the multiplying by a factor of 2 inside of the function is going to compress horizontally. Okay, so what if we want to stretch horizontally? Well, if we want to stretch horizontally, then it's just going to be the other case from the numbers that we use for a vertical compression. So it's kind of opposite here. Horizontal stretch comes from values that are between 0 and 1. So like half. If you want to stretch horizontally by a factor of 2, put a 1/2 inside of the function. Okay, and that's what I did here. Y equals the square root of x is the parent function. Uh, oops. And I was calling it f of x. No big deal, but f of x equals the square root of x is in blue. And f of 1/2 x is the square root of 1/2 x. And so why does this stretch horizontally? Well, the point 4 comma 2, um, if we want this same y value of 2 in this new function, remember we had to plug in 4 into the basic square root of x function because the square root of 4 is 2. What do we now have to plug into this 1/2 x? No matter what number we plug in for x, the 1/2 is going to cut it down to half of its size. So if we want to get an output of 2, we want the argument to be 4, but if it's going to be cut in half, if my x value is going to be cut in half, I need to put something that's twice as large. So uh, f of 1/2 of 8 is going to be the square root of 1/2 times 8, which is equal to, so my input is 8 here. My input is 8. When it gets divided by 2 or cut in half, I get the square root of 4, which gives me a 2. So the value 8, the input 8 produces a y value of 2. So I needed an input that was twice as large to produce the same output to keep the y value the same, my x value has to be twice as large. And so what that's going to do is increase the x values by a factor of 2, and the y value stays the same. So that is a horizontal stretch by a factor of 2, even though we used a 1/2 is what did it. A 1/2 caused the x values to all need to be twice as large to have the same y value. Okay, so this is a horizontal stretch, and we just went over the compression as well. Okay, and I didn't put the negative case here, but if a was less than -1 instead of greater than 1, if it's less than -1, it's going to be compressed horizontally and reflected about the y-axis. Okay, and we showed pictures of that there. Let's go ahead and take a look on Desmos here. We'll put the A, let's put it at 1 here just to kind of see. And there we go. So if we increase, let's say we increase A to be equal to 2, normally I would think that would make it twice as large, but because this is a horizontal transformation, it's going to be, kind of counterintuitive. So instead of stretching horizontally, it's going to compress horizontally. And so let me increase it. This green graph, um, and it may be a little bit hard to see, but let's see if I can actually, yeah, let's do that. Here, give me 1 second. Um, and let me put something like uh, 2, comma, f of 2. Um, Let me use 4, f of 4, just to make this a little bit, see if this looks better. Um, and hmm, yeah, on the spot here, I can't think of how I would show this. Um, so one thing that it looks like when I increase this, it actually looks like well, yeah, a horizontal compression can look in some cases like a vertical stretch. It looks like it might be moving up, but it's actually not. Well, we don't have to think of it as moving up, but the graph moving in the horizontal direction, being compressed towards the y-axis. Okay, so I was trying to follow a point here. Um, just like I showed, let's say here, the 0.42 became the 0.22. It got, compressed inward. And so if we go to A equals 2, we can see that point there. This red point moved in this direction um, towards the 0.22. Okay. All right. Um, and so let's go ahead and take a look. What if A is between 0 and 1? Well, that's going to stretch this uh, horizontally. And it is going to look like, it's actually looking like it's going down, but it's actually, you can imagine the values being pulled away from the y-axis and it being stretched horizontally. If you stretch it horizontally, that's going to look a lot like a compression, a vertical compression. But they are different. Um, they are different, and it does matter for some graphs, but they look very similar in this case. Okay, and then if A was a negative value, well, it's just going to be reflected about the y-axis. All right, so that is a summary on all of the transformations that we have. And so now we can kind of mix them all together and, in the problems that we have. So I'm just going to continue this video. I had to do this introduction because, um, well, it's a lot of necessary information in order to do the problem. So let's go ahead and jump into the problems now. This is worksheet number 2. And let's go ahead and take a look at um, yeah, let's take a look at one of these problems here. I've graphed something in blue, and that's what I'm going to be using my doing the transformations on. So let's go ahead and I'm going to draw a table of values for my blue graph. And I think it has 4 points on it. Yep. So these points have coordinates um, -4, comma 0. The other point has coordinates -2, comma -2. We're at 0, 0 at the origin for one of the points, and then finally 2, comma 2. Okay. And so I'm just going to use this. So suppose that this graph in blue is y equals f of x. And so what is f of x minus 3 plus 1 going to look like? Well, we know that this plus 1 is going to translate my graph up 1 unit. And this x minus 3 inside of the function is going to translate my graph which way? The minus 3 goes to the left? No, it goes to the right, 3 units. It's always kind of counterintuitive, but for a similar reason, I don't want to get too deep into the explanation to make the video too long, but um, yeah, so we'll just skip it over, and you can watch the other video if you like. So the minus 3 inside of the function goes to the right 3 units. Okay, so if I'm going to go up 1 unit, then that is going to increase my y values by 1. So I'll graph this in green here. The new function, 1, 2, 3, 4. So all of my y values from before, I'm going to add 1 to them. So 0 plus 1 is 1. -2 plus 1 is -1. 0 plus 1 again is 1, and 2 plus 1 is 3. And if I'm going to move to the right 3 units, to the right 3 is increasing the x values by 3. And so these original x values are going to increase by 3. I'm going to add 3 to each one of them. So I'll start with a -4 and add 3 to it. -4 plus 3 is -1. -2 plus 3 is 1. And 0 plus 3 is 3. 2 plus 3 is 5. These are my new points. My function y equals f of x has been transformed into this f of x minus 3 plus 1. And the points on that new graph are -1, 1, 1, -1, 3, 1, and 5, 3. And I can connect the dots just like they were connected before. Is that true? Well, let's see. This is my original graph right here. And what I said, I shifted this 3 units to the right and 1 unit up. 1, 2, 3, 1 unit up. Boom. They do coincide. Yes, so that graph in green, let me actually delete that. That graph in green is the new transformed function. Okay, so that's nice. How about 3f of 2x? What is this new function going to look like? Well, when we multiply inside of the function by 2, that's a horizontal transformation. Multiplying by a factor of 2, we said that's going to be a horizontal compression. And since it's compressing, it's going to divide all of my x values by 2 to half of their size. So I'm going to take all of the x values from the original graph and divide them by 2. So here I'm going to just put an arrow to show I'm dividing this number by 2. So -4 divided by 2 is -2. -2 divided by 2 is -1. 0 divided by 2 is 0. And 2 divided by 2 is 1. Okay. Okay, so that 2x is going to compress horizontally, divide the x values by 2. And then what does the 3 do? Let me draw that in purple. This 3, when we multiply by a number outside of the function, that's going to change the y values, the function values, to 3 times their size. So this is going to be a vertical stretch. This is going to multiply y values by 3. Okay, so I'm going to take these y values from before and multiply them by 3, triple them. So 0 times 3, negative 2 times 3 is negative 6. 0 times 3 is 0, and 2 times 3 is positive 6. So let's graph. Negative 2, 0, negative 1, 1, 2, 3, 4, 5, 6, 0, 0, and 1, 6. Whoa. Okay, let's see. Does this make sense? Well, at least in terms of if we take the original function and put it here where it was, did this graph get compressed horizontally by a factor of 2, get cut down to half of its width? The answer is yes. And then did it get stretched vertically by a factor of 3? Yes. So that purple function is the new transformed function. All right, very good. Um, let's go ahead and continue, just because I don't want to make a new video, start a new video when we have all of this, so if you're just jumping to see problem number 6, there's a whole lot of prerequisite information that you need to cover first that we went over in the beginning. So let's go ahead and just continue here. We'll do 6 and 7, and then problem number 5 is 4 as well, since that's on the same topic. All right. So, and we'll try to go somewhat quickly here, but so do watch my other video. This is kind of just to give you the, idea. I'm going to do these problems here that I've just kind of made up, and you can try the other ones on your own. So, how do we do these highlighted problems? Well, we kind of showed the way of doing it, one way of doing it, with this previous example, number 5. What we can do is we can see that all of these are square root functions. And so what we need to know well is the parent square root function. This is f of x equals the square root of x. We know that this function has the points, let's say 0, 0, 1, 1, 4, 2, and 9, 3. 9, 3 is actually going to be off of the page here, so we'll only use, let me cross this out. It is part of the graph, but we're not going to use it. So in blue, I will graph this. And I want to show how fast we could do this problem um, if we know function transformations well. So here's the parent function. What do these transformations do to the square root of x? They shift, let's see, -1 goes to the right. Always got to think about that. Right 1 unit. The +2 goes up 2 units. And so all I'm going to do is take these 3 points that I've graphed in blue and shift them all to the right 1 unit and up 2 units. And that is our new graph. So to the right 1 unit and up 2, would put my origin point there. To the right 1 unit and up 2, we'll put this point there. We know that this graph starts at the origin, so this is going to be where the origin got, moved to. That's our new starting point. There's the graph. It took me, 10 seconds to graph that. If you know the parent function well and you know function transformations well, these problems are, very, very quick. Okay. Next, let's take a look at this one here. This is going to shift my graph 3 units um, to the left. Okay. This uh, 2 is going to vertically stretch by a factor of 2. And so we could actually vertically stretch. We could also take a look at the table. I want to show how quick actually this can be done, and maybe I'll do the table afterwards. So actually I'll leave that off here. Vertically stretch by a factor of 2. All the y values are just going to be twice as large. And then finally the negative is going to reflect about the the x-axis. Okay, so let's go ahead and graph our original 3 points. 1, 2, 3. There's our original graph, our parent function. And in purple, I'm going to shift these points to the left 3. So 1, 2, 3. There we go. But this is not my graph. I've only shifted to the left 3 so far. So let me now vertically stretch by 2. I'll switch to the color black. Vertically stretch by 2. So all of the y values are going to become twice their size. A y value of 0 stays 0. A y value of 1 becomes twice as large to 2. And a y value of 2 becomes twice as large to 4. So here is my graph. And I can actually write the function, I guess, if I want to. This is y equals 2 square root of x plus 3 in black. In purple, I graphed y equals uh, just the square root of x plus 3. Just shifted to the left. So I'm applying a transformation at a time. And then finally, the negative, that is going to go in green because this is my final graph. I'm going to reflect each of these y values about the x-axis. So all of these y values just become their opposite. And so just showing that reflection there, how it's happening. And here we have our graph. Looks something like that. Okay. My final graph, the answer is in green. And notice I'm doing it here, showing kind of demonstrating how to do the problems, but it's very quick. If I was plugging in points, trying to plug in points to figure out what x values can I plug in and what y values do I get, that could take a good amount of time. It can be done that way, but with function transformations, I would say that that will save you a lot of time. All right, and the last one, let's show how quick this can be done. 0, 0, 1, 1, and 4, 2 is my parent graph. What I'm going to do is I'm going to reflect about the y-axis, since the negative is inside the function, and then I'm going to shift that graph down 2 units. Okay, and so my intermediate graph, if I reflect about the y-axis, is going to look like this. You can all see that. And then if I shift down 2, I'm going to now graph in green because that is my final, let's see, down 2 units, down 2. That's just right there. 15 seconds. And that's even drawing all the intermediate steps, which is, yeah, I mean, the green graph is my answer. Okay, so nice. Now let me show how to do one of these um, you know, let's show another way. There are a couple of ways that you could do these problems, but let's show with this last one here how else we could do the problem. If we know the parent function very well, so here are the values, the x and y values of the parent function. Now, what's my, you know, other function going to look like? My transformed function. Oops, left a big space, but that's okay. Well, if I reflect about the y-axis, that is going to require me to multiply my x values, multiply x values by -1. So we can call this the table method. We're going to look at a table of values for the parent function, and then we're just going to multiply the x values by -1. And then here for this down to, well, if I'm moving down, the y values are being affected here. The down to requires us to subtract 2. So I'll put minus 2 from y values. Okay. So let me multiply these x values by -1. They're going to become 0, -1, and -4. And then subtract 2 um, from the y values. So -2, 1 minus 2 is -1, and 2 minus 2 is 0. And notice that these are the exact same points that I've graphed. -4, 0 is right there. -1, -1 is right there. And 0, -2. So if instead of imagining, the reflections and the translations happening, we can just use the table, transform the x and y values, and then just plot these points and then sketch our curve. So that's another way to kind of go about this. Um, this 3 to the left would require us to, if we're moving 3 to the left, we would subtract 3 from each of the x values. And then we would multiply the y values by 2 to make them twice as large. And then we would multiply all of the y values. If we're reflecting about the x-axis, the y values are all switching in sign. So we would multiply the y values by -1. Okay. All right, so you can make the table for that one if you like, and make sure that that table comes up with, these 3 points that match up with these 3 points here. All right, moving on. There's a lot, to cover here, so um, we'll we'll move on. All right, and this is going to be very similar here, but in problem number 7, it says graph each transformation of y equals the absolute value of x. The absolute value of x, if you want to look at a lot of detail on that, you can see my other video. But the function looks something like this, -2, -1, 0, 1, and 2 for the x values. And the absolute value of that x value is just going to be 2, 1, 0, 1, and 2. And so we can plot these points. Oops, plotted one too many, but it's going to look like this. Okay. All right. And so now all we're going to do is transform this graph using some sort of transformation that are indicated by these functions here. And so again, we'll do these 1, 2, 3 problems. Since this video is about an hour long here already, we'll just do it very quick. Um, this is going to go up 3. Um, and really, actually, I like to start, maybe I should go back. I like to start as close as I can to the x, to the variable. If I was plugging in a value, the first thing I would do would be to add 2 to it. So I really should reference this transformation first. Then we would take the absolute value of that sum. And let me show what I mean here. So let's just plug in the number, y equals negative, the absolute value. I'm going to plug in 0, let's say. 0 plus 2 plus 3. What's the first thing that I would do when simplifying this expression? I would add 0 and 2 together. So that's why I should first um, do the transformation of the 2. Then I will take the absolute value of 2, which is just 2 itself. Then I'm going to apply this negative to that 2, which is going to give me a -2. So I will apply the transformation of the negative next, and then I'm going to add 3 finally. So then I will add or apply that +3 transformation last. Okay, so I'm going to do them in that order. And so the +2, always get confused here. +2 is not to the right, but to the left. Left 2 units. And then I will apply this negative. This is reflect about The negative is outside of the function, which is a vertical reflection, which is about the x-axis. And then finally, the last one here is a plus 3. The whole graph will move up 3 units. Okay, so let's move each of these points to the left 2. 1, 2, 1, 2, 1, 2, 1, 2. So here's my intermediate graph. Looks something like this. That's left 2. Reflect about the x-axis is going to reflect each of these points, looking something like this. And then finally, up 3 units. If I move it up 3 units, I'm going to put this in green now. 1, 2, 3. 1, 2, 3. So if I move them all up 3, this is what my function is going to look like. Um, and let's make it look a little symmetric here. Okay. All right, very good. Let me do this one here without really saying much. Well, let's see. Yeah, none of these are going to be. Okay. Uh, so parent function looks like this, and it really goes on forever. If we wanted to, this thing has a slope of 1 or -1, like that. So that plus 2 is going to go to the right 2, and then down 1. So let me actually do that here just by shifting this whole thing. Plus 2, be right here, down 1. And the only thing left to do is to um, stretch it vertically. And I've already messed up my own rule here. We can finish this problem actually. All we need to do now is stretch it vertically by a factor of 2. So let me graph this um, in purple to show this point down here. It has a y value of -1, so I'm going to double that. The value of 0 is going to stay 0. The value of 1 here is going to become, oops, and that's, the value of 1 is going to become 2. The value of 2 is going to become 4. And my graph is going to look something like this. Yep. And the reason I kind of said, oh no, I kind of made a mistake. Well, it wasn't really a mistake, but I didn't go according to my rule that I just mentioned in the previous problem. Working from the inside and working my way out, I should have first gone to the right 2 and then stretched it vertically and then shifted down 1 unit. Okay, um, it would arrive at the same function that I have graphed there in purple. But I actually do prefer to do it, in terms of the order of operations. So uh, since x would be subtracted by 2 first, I should go to the right 2, and then the 2 would be applied before this -1. So I should vertically stretch by a factor of 2, and then subtract 1. Okay, but I'll leave it like that. That's okay. All right. Finally, we can do this last one here. This is going to shift left 1 unit. Then I will reflect. Um, Reflect about the x-axis. And then finally, down 2. Okay, so um, my parent function looks like this. Left 1 Okay, where's left one? I'll just put the dots, but I won't graph just yet. That's left one. Reflect about the x-axis. I'll graph these in black. There it is, reflected about the x-axis. And then down to, each of these dots is going to move down 2 units. Here's my graph. That's quite fast to be able to graph that there. All right. There is one more problem that we'll do. Problem number 4, I think it is. This one here is just taking a function. So there's a function right there, f of x. I'll use f of x equals negative 2x squared plus 3x minus 5. And we want to shift this function 3 units down. How do we shift this new function? So how do we produce a new function that is just f of x shifted 3 units down? Well, let's call it g of x. That's what it asks us to do in the prompt. G of x is just going to be the function f of x shifted 3 units down. We just subtract 3 from the function. Okay, so that's going to be negative 2x squared. It's going to be f of x, which is negative 2x squared plus 3x minus 5 minus 3. And we can combine like terms there. The negative 5 and the negative 3 gives us that g of x is equal to negative 2x squared plus 3x minus 5. No, not minus 5. Minus 5 minus 3, which is minus 8. And since we're towards the end here, why not? Let's graph this just to see. Did I produce? And this is actually, a Desmos is a very good tool when you're doing your homework, or negative 2x squared plus 3x minus 5 was the original function. There it is. And so is my function, the one that I gave, just the original function shifted down 3 units? We'll find out. Yes, it looks like it's just 3 units lower. Okay. Oh, yeah, at least that point. The x value is the same, y value is 3 units lower. That's true for every point on the graph. All right, nice. Let's look at one that's a little bit more complicated, and this will be the last one. And we're doing the problem here that I've written down, that it's highlighted. We're going to take the function that's given in the prompt, f of x equals x squared plus 3, and we're going to shift it 2 units up and 1 unit to the right. Okay, so if we looked at the notation from the previous PDF that we were looking at the beginning of this video, um, that is going to be, well, let's see, g of x is going to be just the original function shifted 2 units up. I missed a little bit here. Up. So that's going to be, and 1 unit to the right. Well, we know to go 1 unit to the right, we need to do something to the inside of the function. To go to the right, we subtract 1 on the inside of the function. And to go 2 units up, we add 2 to the outside of the f of x, outside of the function itself. And so, okay, well, the function here is the squaring function, x squared plus 3. And so if we're going to plug in x minus 1 into this function f of x, then this is going to be x minus 1 squared. We're going to put this x minus 1 into the function f, which is this here, this x squared plus 3. And so then we have our plus 3. And then the plus 2, we need to apply it to the outside of the function. So we'll put plus 2. This is my g of x function. Okay, so is it true that g of x equals x minus 1 squared plus 5? Is this function the same as f, but just shifted 2 units up and 1 unit to the right? Yeah, look at this value here on the outside. The value on the outside is 2 units more, so the y values of g are going to be 2 units greater. And inside of the function, we have a minus 1 compared to the original function. So that minus 1 is going to shift to the right 1 unit. Um, and so we can graph it to check, but yes, that's g of x is the function that we want. Shifted 2 units to the right and 1 unit. Oh, sorry, 2 units up and 1 unit to the right. 2 units up, 1 unit to the right. Yes. All right. So you can try these other problems, the ones that are actually typed on here. I changed them slightly. Try these yourself, and then we'll check our answers. Um, Try all of these, if you have time, and then we'll check our answers when we meet up. Okay. So remember to leave a like on the video or put a comment or something. These videos do take a lot of time. And so if you like the videos, like the video or leave a comment. Just let me know. Maybe you have a constructive criticism you'd like to leave. Feel free to put it in the in the comment section. All right. I'll see you in the next video where we will discuss the rest of this, which is linear functions. All right. See you then.